So this course is called Challenges of Object-Oriented Programming. We will discuss object-oriented programming, which I hope most of you know what it is, right? So raise your hand if you don't know what is object-oriented programming. So you do. In this course, I will try to show you that you don't, and I don't understand it. So we will together see what are the challenges of it, why it's difficult to understand. Before we start, this is the structure of this lecture. We will discuss the history, a little bit of object-oriented programming. It's interesting. I will try to make it interesting. Then we'll discuss what was the original idea of object-oriented programming, why it was created. Then we will compare the thing which is called object thinking. That's the idea which changes the way people write object-oriented software. And then we'll discuss the problems. Then we will, in the end, I will explain you what to do in order to pass the exam and what is expected by the end of this course. Before we start, that's a disclaimer. It's a warning for you. I wrote it myself, then I asked ChatGPT to rewrite a little bit, so now it sounds very academic. The bottom line is this. Everything I will tell you in this course is very subjective, very opinionated. So this is my opinion. So if you take this information and go to the company where you're going to work, and then you will try to apply it to your everyday work, you may get fired for this. So be careful. So I will show you a little bit, not a lot, different understanding of object-oriented programming, of how software should be written. You may use it in your real life, or you may ignore it. It's up to you. So this is not the ultimate, the absolute truth. This is the opinion of everything I will tell you in this course. So that's why it's an elective course, not mandatory for you. So if you decide to listen to me, so listen. Maybe it will help. It helped me a lot. I came to this after, I think, 15 years of programming. I started from non-object-oriented programming style a long time ago. Then I moved to C++, to Object Pascal. I was using objects for many, many, many years. And then I understood that I was doing it wrong. And I changed the way I was using objects. And now I use them differently. Now I use object-oriented programming differently. And I will share with you how different it is. Maybe it will be useful for you. Maybe you will like it. But again, be careful. Don't just go around and tell everybody that this is the right way, because many people will disagree with you. And I know many stories where people actually try to do it in their own companies, and in the end, they get into trouble. So, start with the history. So how it all started. I was preparing this lecture. I didn't really know everything, like the whole history, so it was also interesting for me. It seems, this is what Wikipedia is saying, it seems that object-oriented idea, the object orientation, started somewhere around 1961, 1962, so it's about, how many, 60 years ago. I was not born at that time. And this guy, Ivan Sutherland, he created an application, a software, which is called Sketchpad, where it was possible to draw something on the screen, which was a huge surprise for humanity, because we were not using screens for that. So he was showing how you can draw something on the screen, and then you can move the elements on the screen. So you can just take the element and move the pointer, and then the element goes together with the pointer, and everything inside the program was represented as an object. So it was an idea, how about we group all the elements of this figure and say this is an object. So that was, they say, it's in the beginning of object-oriented programming. He was calling objects, they're called occurrences, and their prototypes, they're called masters. So there was not object-oriented, it was called master and occurrence, different names. But the idea was around that. So it was not yet a language, it was just an application. And then a language showed up. A language was created. The first object-oriented programming language was Simula. Simula was developed in 1965 by these two guys in Oslo, in Norwegian Computing Center. So they introduced classes, inheritance, virtual methods, subclasses. These things you probably know. Classes, this is what we use. So they, again, about 55 or something years ago, they suggest, how about we have classes in our application? Before they had the language Algol, so on top of Algol, they introduced classes. Let me show you an example of Simula 66. So this was the language, this is how it looked. I never programmed Simula, but if you look at the code, it looks indeed quite easy to read for people who are familiar with C++ or Pascal. It's close to maybe to Pascal, in my opinion. So you see, first they define the class figure, and then they define the class circle. So the circle inherits from the figure, and that's a virtual method which is called square. Here, the method square, and this class inherits, maybe I'll sit down already. So the class circle inherits from the figure. So there are two classes, 1, 2. These are the attributes which are encapsulated in the class circle. That's the body of the class. They have the procedure. They call it procedure, not method, but procedure. This is the name of the procedure. I'm just reading it, and I never programmed this language. I'm just reading what I see on the screen. And then, in order to return the square, look at how they do it. So in order to calculate the square of a circle, they multiply the radius, which is r, they multiply by p, and they assign the result to the name of the procedure. That's probably the father of all object-oriented programming languages. So they separated, I'll explain now what it was done for, not now, a little bit later. And then object-oriented programming term was coined. So who introduced the name object-oriented OOP, or OOP, sometimes they say it. That was Smalltalk programming language, which was created in California in Xerox Park Research Center. I think RC stands for Research Center. And Alan Kay was the main guy. Here's in the middle of the picture, this guy in the white t-shirt. So Alan Kay was the father of this term of object-oriented programming. He introduced the name. And they created Smalltalk. Smalltalk, again, new programming language, which of course was influenced by previously existed languages, but it was quite a new language. This language really introduced something new, which still remains sort of an iconic object-oriented programming language. This is an example of the code. Again, I wrote this. It seems to work, but I never programmed Smalltalk. So look, here they define a class account. There they define the attribute balance, and then the account, this is the definition of the method new. So you can say account new like this, account new, and inside the account new they call super new. The idea of this language is this. The idea is that in order to make a call to an object, you write it like this. On the left side you say the name of the object, and then the space, and then you give the name of the method which you call. So this is basically account.new, something like this. Or you can say a deposit and this, and then the semicolon, and then the argument. So here you call deposit on a, and the argument goes 42. And since there's only one argument, so you can say, for example, if there are two arguments, you can say a deposit semicolon 42, the currency semicolon United States dollars. So all the parameters, they go after the object which you call with a space, and then they call it sending messages. So in Smalltalk, they don't call, they say that they are sending messages to objects. And they say it everywhere. So when you read about Smalltalk, they say object-oriented programming is about sending messages. It's not about calling. It's not about calling functions or methods. It's sending. So these are the messages they send. So they say, here we send the message. Here we send the message. And the object which receives the message is supposed to reply. But in reality, it's, you understand, technically it's the same. So you just make a call and then the result comes back, like you call a normal function. So that was interesting at that time because objects didn't exist at that time. And the idea of messages was quite fresh and the syntax was quite revolutionary. Like this extension, you see the account, now you extend the account. So first you define the class account and then you extend it. So you say, how about we add more stuff to the account, which is, for example, not possible in Java or in C++. In Java, you define the account once. You just say, this is my class, and everything goes there. You cannot say, okay, later I have something more to add. Here you can do that. You can say account extended. So how about you put deposit message receiver or method for this. So that was Smalltalk. And then just look at the name. So the Smalltalk was introduced in about 1960, I don't know, 68 or something, and that maybe 70, maybe I'm wrong, 70 something. And then people started to complain about object-oriented programming. I will give you a number of quotes now in the further slides, but look at this one. That was 1982. Long time ago, and just a few years after Smalltalk was introduced. So this guy, I unfortunately didn't find his picture, so he says, everyone will be in favor of object-oriented programming, looking into the future. Every manufacturer, blah, blah, blah. Every manager will be glad to use it. Every programmer will practice it, and no one will know what it is. Just like I started this lecture. I said, do you know what it is? You said, yes, you do. And I told you, I don't. They didn't. 50 years ago, they said, we don't know what it is because they throw an idea into the crowd, and then everybody understood it differently. Every programmer will practice it differently. So, and then it was still academic. This open object-oriented programming was still an academic. Smalltalk was an academic, mostly language, to my knowledge. It was not like publicly, it was not used by real practical programmers everywhere. And then who made it popular? Who made object-oriented programming really popular for all of us, for practical programmers? That was Bjarne Stroustrup. Who ever heard the name of this guy before? You did. So he is the father of C++. He invented C++. He took C programming language and extended it with the features from Simula. So he said, how about classes? C didn't have classes, so he introduced classes into C. And then C didn't have inheritance for the classes. Okay, he introduced inheritance. And so on and so forth. So he extended already very popular language. C was very popular at that time. People really used it to write practical software. So Bjarne Stroustrup made an extra step and made a language which was easily adopted by the community. By the way, I interviewed Bjarne last year, and you can watch, I'll send you the slides, you can watch the interview with him. He's now much older than me, and he is definitely a father of C++. So he made it popular. He made this language, this idea popular. Everybody started using C++. This is the example of C++ code. Again, we have a class figure. In this class, we have a virtual method square, and then the circle extends the class figure. This is the constructor. In the constructor, we encapsulate the center of the C and the radius, and then the square. In order to calculate the square of a figure, you return the p multiplied by the same code, but in C++ syntax. I'm sure this is much more familiar to you who ever tried to use C++. C++ now is one of the top languages on the market. And then people started to complain even more. For example, again, this is the quote. They say there are as many definitions of object-oriented programming as there are papers and books on the topic. So again, people don't know exactly what it is, and I'll show you now why people are so confused. That's a very famous quote, very famous, but by this guy, I told you about him. He was the inventor of Smalltalk, and then he was speaking at the Object-Oriented Programming System and Languages and Architectures Conference. It's very popular, Uppsala. In 1997, that was right. How many years? In 1985, C++ was created, and he was speaking in 97. So it was, 12 years after C++ was introduced. And he said, I made the term object-oriented, but I can tell you, I didn't have C++ in mind. So it seems that C++ went away from the original idea, according to this guy. So they meant something different. They meant object-oriented programming differently. But C++ made it wrong or different. What
was on the mind of Bjarne Stroustrup when he introduced?
That's the question we're going to discuss in the second section. Yes. So what was the original intent and why the C++ was so different? Why Bjarne did it the way he did it? That's a big question. He actually was asked about that in multiple interviews, like why exactly C++ was made that way. But in my opinion, is that he was interested to make it practical. He was interested to put this academic idea into practical implementation so that programmers can start using it. So he took existing language and a little bit extended it, because C++ was not immediately created the way you have it now. C++ even is being developed even now. You know, the different versions of C++. We have C++ 11, C++ 17, C++ 21. So C++ is changing every few years. So he introduced, I believe that initially C++ didn't even have, I may be wrong, but they didn't have templates originally. So that was introduced. Yeah, I'm right? Yeah, so that feature was introduced later. So initially he made a language which was not as powerful as it is now. So he just made something which looked like similar and worked like C. And actually he won. Actually he achieved a lot, because actually his language became popular. His language is one of the top languages in the world. Smalltalk is not.
But his implementation was based only on his opinion. Right?
His opinion, mostly, yeah. To my knowledge, yeah. To my knowledge, he just, of course, he knew about similar. He got a. He's a PhD, so he's academic. He's coming from academic environment. He's not just a coder, so he knew about object-oriented ideas, but he somehow interpreted it for his own implementation. So Alan Kay, 12 years later, said, "I don't know what you guys are doing," basically. So I didn't mean that. I meant something else. Actually, we also had a conversation with him. I have a blog post, I wrote a blog post, which is called "Alan Kay was wrong about him being wrong." So where I argue that his interpretation of objects, and because he said later that he was wrong about objects sending messages, and I said, "You're not wrong, you're wrong saying that you're wrong." And we had a debate with him on so if you're interested, you can read. I didn't record an interview with him, but small debate. So what happened later, after C++ was introduced in 1985? So what people are complaining about is the variety of languages which were created. All of them are object-oriented to some extent. Some of them are not exactly like Haskell, for example, or for example, JavaScript, or what else? The Erlang, for example. So these languages are not directly positioned as pure object-oriented languages, like, for example, Self, or like Java. So they say we are or Ruby. So they say we're pure object-oriented languages. But these other languages, they have a flavor of object orientation. And there were many of them. Look at the years. That's when they were created. So the top years, the most actively, the years where languages were created. Look, 1993, 95, 95. I'm actually surprised when I was writing this. I was surprised that in 1995, 4 languages were introduced, quite popular. Java, Ruby, JavaScript, Go. So all of these languages at the same year, and all of them object-oriented. And all of them have different features. So if you look at this Java, what Java can give you, how Java understands what the objects are, and what JavaScript will tell you about objects, it's going to be completely different. Two completely different understanding of what is an object. So they made it the same year. So original idea was something, and we will discuss now what it was, and then it went into different directions. And again, some quotes. They say there is no uniformity or an agreement of the set of features and mechanisms that belong in object-oriented language, as the paradigm itself is far too general. So we just say object orientation is about having objects and classes and subclasses and methods and inheritance, and it's too general. We don't understand how exactly it should work. So this is incomplete list of features which you can find in object-oriented programming language. So no need to read this, it's just a long list. Actually, I got this list when I asked ChatGPT, what object-oriented features do you know? So ChatGPT gave me this list. I actually asked it a number of times. So I asked first, it gave me like 10 features. Then I asked, okay, give me more, it gave me more. Then I give me more, it gave me more. So it was giving me more and more until it started giving me some garbage. So that's the list I collected. So there are many features. And if you take one language, for example, JavaScript, then you will not find many of these features there. If you take Java, you will not find other features there. So each language gives you some features. So the question is, what exactly is object-oriented programming? We don't know. And a few more quotes, and then we'll go to the main question of what is the intent. You probably know this guy. Do you know his name? He's a probably the father of computer science, I would say. He says object-oriented programming is offered as alternative to correct ones. And also he says object-oriented programming is an exceptionally bad idea which could only have originated in California. He probably refers to Smalltalk. So I mentioned to you that Smalltalk was created in Xerox Research Center, that was in California. So, and this guy, he lived in Amsterdam, in Holland. I'm not sure about Amsterdam, but in Netherlands. So definitely he complains about his friends on the other side of the planet. So, but he complains completely about everything, not about how C++ did it, but he says the entire idea is bad. And not only him. You know this guy, right? He hates C++. Everybody knows about that. So entire Linux operating system is written in C, not in C++. You cannot find C++ there. It's pure C. The entire Linux kernel, I'm not sure about applications, but Linux kernel is written in C language. And he says C++ is a horrible language. And he says that, in other words, basically to interpret that, he says if you use C++ the right way, as it is understood by people, as it should be, then you get down to C. So you just throw away all the garbage from C++, which normal people should not use and understand, then you will just get down to C language, and that's it. So object orientation is just noise and garbage, which only makes programming more difficult. You know this guy, Jeff Atwood. You know, if you read blogs, then probably the blog number 1 about software engineering is called Coding Horror. You don't know. That's the blog. Well, maybe now it's not, I don't know. But when I was younger, then this was the blog number 1. And he is the co-founder of Stack Overflow. Stack Overflow, you know. So he created this platform, he and his partner, his friend. So he also is not very happy about object orientation. He says that object orientation seems to bring at least as many problems as it solves. So basically no point of using it. And a few more quotes and we're done. These guys are saying that object-oriented programs struggle with increasing complexity. So complexity grows, large object graphs of mutable objects. Why mutable is bad, we'll discuss on the next lectures. But basically object graph means that object inherits another object, they depend on each other, the graph grows, and complexity is too high, we don't understand what's what. That's the end of the story. You know Clojure, right? This is the language. And he is the creator of this language. Clojure is a pure functional language. So maybe he complains about object orientation because he loves functional programming. So to summarize, that's not now my opinion, my personal opinion. The complexity of object-oriented code is the primary drawback, complexity. So when people write object-oriented code in C++, for example, it's difficult. It's difficult to understand. It becomes more difficult than comparing to the code you would write using just C. No objects, no classes, no inheritance, just functions in C. One function calls another function, passes the arguments, returns the argument, returns the results, that's it. So when you introduce classes, then you become your code becomes less maintainable. And of course, the more bugs, more troubles, more problems. So this is the key problem, complexity. I think I have 2 more quotes. So they say, this is just, I just sorted them by the year. So this is just recently. You see, the people are complaining just recently, 2015, it's just 8 years ago. Reading object-oriented code, you cannot see the big picture. And it's often impossible to review all the small functions that call the other functions that you modified. So the objects call objects from all the different places, and it's difficult to understand what's going on. And I think that's the last quote. Just about a few years ago in a paper they published. She says, object-oriented programming promotes ease of designing reusable software, but the long-coded methods, long methods, makes it unreadable and enhances the complexity of the methods. So basically, long methods, complexity. That's the paper is she compares what are the problems which we face when we do refactoring, and the author blames object-oriented programming. So, to summarize before we go to chapter number 2, we don't know anymore what exactly is object-oriented programming because many features in all languages, and whether it helps us write better code. It seems that it doesn't, because so many people say it doesn't, and my personal opinion, it doesn't. Like I told you, my personal story, I was coding in without objects. Well, initially I was coding without objects when I was like you, like student, because we didn't have C++ at that time. Then I moved to C++. I started to use C++ and Java for about maybe 15 years or so, and it was bad. I didn't like the code I was creating. I didn't like it. It was complex, it was difficult to maintain, it was difficult to support, many bugs. And then I changed, I started doing it differently, and I became happy. But many people didn't change. So they still live with the traditional object-oriented programming and they suffer. Okay, clear so far? So this was to show you the problem. Actually, this is the only lecture in this course which is blah, blah, blah. In all other lectures, we'll see the code. In all other lectures, I will open the code. I'll show you the code from popular libraries, Apache, Guava, mostly Java, and I will show you how they do it wrong and how we can do it better. But the first lecture is blah, 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 so I'm trying to trigger your mind that there is a problem. Because most people, when I speak at software conferences, very often people raise their hand from the audience and they say, what exactly is the problem? Why are you suggesting do something differently? We have Java, we code Java for 10 years, everything works. What exactly is the problem? Why you suggest doing it differently? So in order to avoid these questions from you, I gave you this. So people complain that we don't know what it is, we have such a variety of things there, and the complexity is high. So it's not me saying, other people saying the same, many people. All right? I don't have track of time, so if somebody can give me some phone, which I can check time to time. No, but can you put your watch here? Okay, thank you. Perfect, thanks. So, original intent. So what was the idea? So now all of them are complaining, not all of them. Alan Kay said you forgot the original idea, and that's why you're sinners. So what was the original idea? This is my favorite author about object-oriented programming, David West. He wrote the book called Object Thinking. This is the book which changed my mind. So I got this book, I read it, and I understood that a lot of things needs to be changed in my way of writing code. And he said that's his quote, the contemporary, traditional, mainstream understanding of objects, which is not behavioral. So our traditional understanding of objects is not behavioral, is just a pale shadow of the original idea, and even anti-ethical to the original intent. So what we have now, which is not behavioral objects, which I will explain you now what it is a complete misunderstanding of original idea. If you're interested, you can watch. We had a few conversations with David on YouTube. There are 2 links. This is how I understand original intent. This is, I think, what C++ and Java and most languages and most programmers don't understand who write object-oriented code. I understand that a system is a composition of objects that are abstractions which hide data and expose behavior. I was thinking about this phrase for maybe a few days. I was rewriting it, so now this is what I really think. So again, a system is a composition. This is how a system should be designed, any software system which is object-oriented. It's a composition of objects, and now we will discuss every word in this sentence. It's a composition of objects that are abstractions which hide data and expose behavior. So focus on this: composition, abstraction, hide data, and expose behavior. So let's go one by one. First, what is an abstraction? So we want an object to be an abstraction. What is in general an abstraction? I'm sure most of you understand this word, but still I decided to show you. So let's say we have an apple, like a physical apple. So let's forget about programming, we're talking just what is abstraction in general. So let's say we have an apple. So this is the abstraction of an apple. So this is the information which is abstract enough for me to describe an apple. I see the color is red, the weight is this amount of grams, the price is this. So for this conversation, for example, for this particular conversation or for this particular domain, for this place, this is enough for me to discuss an apple. So I ignore a lot of other things. Where the apple was grown, who is the owner of this apple, how many vitamins in this apple, how many, I don't know, is it tasty or not tasty? So I ignored a lot of facts, a lot of information, and this is my abstraction. So abstraction is usually smaller than the real object. It's usually it has less details. And that's why we use abstractions. We don't want to deal with the real object every time because there's too much details for us. So we abstract it. We say, for example, we have students in this room. We don't care their names, we don't care their ages, we don't care the color of their t-shirts, we just say students. That's enough. That's enough abstraction for the university, for example. But for me, maybe the color of your t-shirts is very interesting. So I say, no, this is not a good abstraction for me. For me, I have 7 students with a dark t-shirt and 13 students with white t-shirt. This is more detailed abstraction for me. But it's still abstraction because there are no names of the students. So I still ignore a lot of facts. The same for the programming. So let's say we have a file on disk. And this is, what is this programming language? Who can tell me? JavaScript, that's right. So that's a JavaScript. That's an abstraction in JavaScript of a file on disk. It has 3 attributes. First is the path on the disk. What is the name of the file? Then I have read function and write function. So I can read the file and I can write the file. Can I delete the file? No. It's outside of the abstraction. So I don't need it. Like with the students. I don't care about the color of their t-shirts. Just students. This file, just read and write. No delete. No move. No check the size of the file. This is the abstraction. Understand? That's the idea of abstraction. So abstraction is taking the real object and representing it for somebody with less details. So object, in object-oriented programming, is an abstraction of a real-world entity, like this. This is an object. File is an object. It is an abstraction of something what exists in a different place. Just put it in your head now. Don't try to analyze too much. Yeah.
Does abstraction mostly refers to data hiding rather than behavior?
Like in this example, it both data and behavior. Like for example here, we don't know how to delete. So delete is the behavior which I throw away. I don't need it. And I don't also have the size of the file. So size is the data. Deleting is the behavior, size is the data. I ignore this and that, both. I only have the location and 2 operations.
From your talk, I understood that it is mostly about the data.
Not really. It's not about the data. It's about behavior as well. Yeah, it's about behavior as well, definitely. And here I say we do file.read and also file.read. So look at this. When I call read, I don't want to know how exactly the read will do it. I just say read. Or for example, for the students, I put all the students in this room. I don't care how exactly they walk in, how exactly they sit in the chairs. Just put the students in the room. That's one operation for me. Everything else is outside of this abstraction. It's not important for me. The same here. So how many abstractions are needed in the application? So look at this example. Look at the code on the left. What is the language, by the way? What do you think is the language? C maybe, yeah, C or JavaScript, maybe C. So look at the code on the left, they do exactly the same. The code on the left works exactly the same as the code on the right. It calculates what it does. Who can tell me? The code on the left, what it does.
The area of rectangle.
Yeah, they calculate the square of I give the 2 coordinates, x1, x1, y1, and then x2, y2, and then it calculates what is the square of this rectangle, right? So it first it calculates the width, x2 minus x1, then it calculates the height, y2 minus y1, and then it returns the multiplication. Between doing this, it checks if the width is less than 0 because the coordinates can be positioned differently. So if it's less than 0, then it multiplies by -1 in order to have widths and heights both positive. Well, if I don't do this, then possibly square will return negative number, right? So we don't want that. So that's why we normalize the widths and the heights. It don't pay attention to the functionality, just pay attention to the abstraction. So we call it, we programmers, we say that square is an abstraction of the rectangle square calculation algorithm. So when somebody will call square, this guy will not be concerned about how you calculate. It just says, give me the square. And all the details are going to be inside this abstraction. We abstract away the calculation. For me, it's just one point of axis. Just calculate the square. Here, we have two functions. One is also the square, and I introduced two supplementary functions we call distance. So in order to calculate the distance between two coordinates, right and left, I do right minus left, and I normalize the distance and return the distance. It does exactly the same. I calculate distance here, multiply by distance here, and return result. Now we have two abstractions. This one is the square, and this one the abstraction of the distance. One abstraction is calling another abstraction. So one abstraction is based on another one. So this we call a higher level abstraction, and this one is lower level abstraction. It's like I call the leader of the group and say, collect me all the students in this room. And these guys start telling, hey, you enter and sit down here. You enter and sit down there. So this guy is doing also some abstract operations. It doesn't tell students, please walk left, right, and then it doesn't matter. I just tell you, just walk in and sit at this place. But for me, this even doesn't matter. For me, just put the students in the room. I give one instruction, and for me, it's done or not done. For the guy who positions students in the room, there are 15 operations. And each operation, again, is abstraction. But if you, I don't know, if we go to the lower level, to the individual student level, then for individual student it matters. How to walk in, how to find the chair, so it's an even lower level of abstraction. So how many abstractions are needed? That's a big question when you design the software. You can design everything like this, like the left algorithm. Everything will be on one level of abstraction, long algorithm, doing everything. And when you as a programmer will look at this algorithm, it will be long method, everything stays on the same level of abstraction. It's like imagine me, instead of having a guy who positions you, I will come to each student individually and say, please move the left leg forward, move the right left forward, move the chair, sit down, next student, next. That'll be boring for me, right? Very difficult. I will stay at one level of abstraction. Everything will be in my control. That's wrong. We don't do this. We want different levels of abstractions. And the more we have of them, the easier to design the software. That's the idea. So look at these levels of, this is the higher level abstraction, square, and square calls distance, distance. So we have two levels of abstraction. So when you design the software, this is one of the primary questions for the software designer. Which levels of abstractions I need? How many of them? And if you make a mistake there, then sometimes you will need to, it happens in the wrong design, you will make calls from lower level abstraction to higher level abstraction. And that's completely unacceptable. So it should be always the software should go from top to down, top to down. Second question, what is data hiding? So remember, the object is an abstraction which hides data and expose behavior. So the question is, what is data hiding? It's a key idea of object-oriented programming, hiding data. It was originally, in an original intent. So look at the code on the left. I say f is new file, then I encapsulate the location of the file. Then I say p f get path. So I take the path of the file out of this object. This is Java, by the way. And I call 5utils delete file and provide the path right here. This is called data escapes the object. So we have an object, we take the data out, and we use the data. This is called escaping. So it's not data is hidden, data is visible. So anybody from the outside can call this method get pass, take the data, and then use this data as that person wants. This is data hiding on the right. Look, we also create a new file. Then we say f delete, and then we assert that that was deleted. So we now don't know, we don't take the path away from the file, away from the object. We just ask the object, do something which we need. So data hiding is done better on the right example than on the left example. You cannot hide data completely. For example, here I intentionally made it, the Boolean is returned, so you see that done is returned, and then we assert that done is actually equals to true.
So this is also data, right? This is also data which is jumping out of the object. So it is impossible to completely design an object which never returns data. It's not possible technically in programming. But we need to try to hide as much data as possible. We need to hide them so that these things do not happen. So this is completely wrong, in my opinion. This is completely not, and this is anti-object-oriented programming. When you let somebody know what's inside your object, instead of letting them ask your object to do something, you just say, hey, take my data and do something with them. You want to know where's my file? Okay, sure, take it, and then delete it. I don't care. So your data is something that you need to hide, protect, and never return, as much as possible. As much as possible. But most people don't do that. Most people let this data go out, and this is what David West is complaining about. He says, the mainstream understanding of object is non-behavioral. Non-behavioral means exactly that. So instead of behaving, instead of deleting the file, the object just says, hey, take my path and go and delete it there. I don't do it. I'm lazy. I am non-behavioral. I don't behave. I don't have any behavior. I just give you the data. And many people design objects like this. They think that object is a container of data. Even there's a name for that, data transfer objects, if you know this design pattern, DTO. And people use it very often. So they just put the things, many attributes in an object, and then other clients just come to this object, take this data when they need it, and use the data. This is called non-behavioral design of objects. And what it's coming from the violation of this idea, the data hiding. We need to try to hide data as much as possible. That was the original idea. Number 3, what is behavior exposing? So we hide data, but we expose behavior. So again, it's related to data hiding. So look at the example on the left. There are 2 examples, they do exactly the same. Functionality is the same. Look, here we define the object user. By the way, what is the language? Who knows? JavaScript, that's right. So this is the user we define here with 3 attributes, login, password, and age. And there's a function which expects user probably to come in, and the function says print console log, hello, user.login, you are something 32 today. And then you say print user. So probably you already understand that this object is non-behavioral because the object let the function print take the data out and then do the printing. Look at the object on the right. The object on the right encapsulates the function print. So now this function print does exactly the same internally. So now on the surface, we call it like this. Here it was like this. Here it is like this. It prints exactly the same result. The functionality is the same. But this is bad and this is good. Why? Because here the functionality is exposed and data is hidden. Here the data is exposed, the functionality doesn't even exist. The object doesn't have any functionality. It's just a container of data. So this is object alive, so it knows how to live. You can send a message to this object, like Smalltalk suggested. So you can say, hey, print yourself, and the object will just do it for you. But the object will never tell you that his age is 32. You're not taking this out. The data is hidden. Of course, in JavaScript, you cannot hide the data. In JavaScript, everything is public, everything is visible. But if there would be Java, you would say this is private, this is private, this is private. So you hide, or C++. So you hide this data and only expose the functionality print. So this is bad design, this is good design. Why? Because behavior must be exposed. Here, no behavior is exposed. So the ideal design of an object which would be working like this, hiding data and exposing functionality, originally was to, again, we're still talking about original intent, remember? So we're still in the chapter 2, it's intent, how they wanted to do it. So the original intent was to have objects look and work sort of like functions, very close to functional programming, very close to functional paradigm. And here on the left you see the functional design with the functions. So square, remember that, square and distance. So we call two distances, and this is the distance function. And we can make exactly the same in Java with the object-oriented style. So we introduce the class distance. The class distance encapsulates right and left, you see, left and right. So we encapsulate this, and then with the value, we'll actually do the calculation and return the value. And this is how we use this distance. So it's very close, a lot of similarities between the object on the right and the function on the left. That was the original idea, how it should be done. So I consider this very good object-oriented code, which is very functional, which doesn't expose any data. You see, you cannot take R and L, the left, right, out, because they're both private. So everything is everything is hidden. The behavior is exposed. So actually, it's not a lot of behavior, actually the calculation. But still, this is the only behavior this small class has. So everything is cool, everything is good. And then people started to confuse things, and I'll show you how. But we need to also understand three things about objects: identity, state, and behavior. Did you hear that before? Identity, state, and behavior. There's just three key ingredients of every object, which an object must have. So look at this. You need to understand this. This is three different things which sometimes people confuse, and they confuse it a lot, and because of this, design suffers. So look at the class on the left. Again, it's a circle. A circle has a radius. A radius is encapsulated in the constructor. Then you can get the radius, then you can set the radius, and you can calculate the square. Simple, right? Very simple class. So look, first, what is the identity? I make new circle and I make another new circle. It's Java. So C1 is not equals to C2. They are two different objects. Identity is different. They are not the same objects. They're different objects. Let's say they stay in the object universe in two different places. They're two different objects. They're not equal to each other. State is what they have, like attributes, let's put it this way, the data, which is supposed to be hidden, but in this design it's not hidden, so you can get it. If you can get it, then you can compare it. So in the same two classes, circle, circle, with the same numbers encapsulated, C1 get radius equals to C2 get radius. So the state is the same, even though the objects are different, but their state is the same. And finally, the behavior. C1, C2, there are two different numbers. Here, look at this, 42 and minus 42, but square here and square there, the same. So you see, identity is the most constrained. Identity tells you that exactly the same, if two objects are equal, if the identity is equal, then we're talking about the same object, the same. Obviously, they will, not obviously, maybe they will not behave the same. So behavior may be different. For example, let's say it's a random number generator. So you take one generator of a random number and then it's the same random number generator. You call it generate me the number and you call it again. So behavior will be different in this exactly the same object. But in this example, behavior is similar, is exactly the same for the different state. So state is different, behavior the same.
But under behavior of random number generator, do you mean
Result produced. Yeah, I mean the result, behavior, like, because we don't know how the algorithm from the surface. If I'm the client, I don't know what's inside. For me, it's an abstraction. So I just call it and say, okay, what's the output? This is the behavior for me. I send you the message, do something for me. You return 55, good. Send it, do it for me. You return me 66. Oh, that's a different thing. I don't care about that. Of course, internally, it's the same algorithm will be. Yeah. So identity, state, and behavior. Every object in every programming language, they have these three things. This is what probably similar in all languages, but some languages they may join. They say, for example, identity and state is the same. They may say they may have such functionality in the language. But Java, for example, they have three things: identity, state, and behavior. And now let me show you how people get confused, how people confuse state and behavior. And that's why they design objects so that the objects start exposing data instead of hiding the data. Look at the design on the left. This is class circle. It encapsulates the radius. You can set the radius, the R, and you can get the R. Very simple data container. And then we have figure utils. And then in this figure utils, you can calculate the square. And you pass the circle here, and it calculates the square of the circle. Who met such utils classes in your real daily life? Definitely. I mean, many people. Maybe some of you do not confess, but many people meet these utils classes. So these utils classes, this is a good example of utils classes. So utils, they exist, or they're also called, that's utility classes. So they exist because we have objects like this. The objects which expose data. So designer of this object believed that returning the radius is the behavior. That the mission of this circle is to hold the radius and return the radius. So that's my behavior. Taking the radius, return. Why not? Right? You can say, this is my behavior. Can it be my behavior? Why not? It's a method, so you call me, you give me something to hold, I hold it for you. You wanted to take it back, I give it back to you. That's my job, that's my mission. That's what I do. Circle. So if we think that holding the data and returning the data is the behavior, then we are in trouble. Then we will design things like this. Then we will make these figure utils. And then we will make, look at this class. This class is definitely so-called anemic object. So it doesn't have real behavior. So setting data and returning data is not it's not a behavior, it's state. It's manipulating with the state. So don't mix the state and the behavior. Behavior is something much more complex than just holding the state. So that should be a clear separation in your mind, that state and behavior are different. But Java will not tell you that. Java will say, yeah, that's nice, you did a good design. No compilers will complain about that. It's only in the hands of programmer. So programmer must understand how much to put into behavior. You cannot just call everything behavior. Behavior is something which is much more difficult, like this. Look at the right example. Here we have the behavior in the class circle. Square, and this is the calculation goes there, and because of that, and here I wrote, look, how to decide what is state and what is behavior. That's a difficult question. But always try to think that the more complex is the algorithm, the better. So if you expose, the behavior you expose should be something meaningful, something more difficult than just holding a piece of data. Because for holding a piece of data, we don't need to make a class. I can hold this in some piece in memory. So if you make a class, if you design a class, then the class should have something which you can say is a behavior, something that behaves, that works, some algorithm. Okay, and final point in this section, in this chapter, and we're close to the end actually. Not close, we have one more difficult chapter. So what is composition? So remember, a software system is a composition of objects which are abstractions that hide data and expose behavior. So we have abstraction, we decided, okay, this is the user, this is the file, this is an apple. For each of them, we hide their data. So nobody can take the price of an apple, nobody can take the location of a file. They can only call these objects and ask them to do something. That's good. Now the final step, how to compose all these blocks into one large system. And this is the composition. And look at the left example and the right example. In the left example, I create a canvas, and then I put on the canvas the circle with the radius 42, and I say canvas, draw. I think it's possible to do it, like some systems do it like this. I can do it differently. I can say canvas is this, and then I say circle, and then I say, hey, circle, draw yourself on a canvas. Can I do it this way? It's also a composition. Which one is right? I don't know. So there is no clear answer. How you compose objects one to another. Who will call who? Who will encapsulate who? The canvas will encapsulate the circle, or maybe the circle will call canvas when it's time to draw something. It depends on many factors. There is no clear answer. But just understand that composition is the decision you make about how objects talk to each other. Who calls who? And who encapsulates who stays inside who? Because here you clearly see that the circle stays inside the canvas. So canvas is like a bigger abstraction, and circle is a small abstraction. It's like a student in the class, or a student in the university. Or maybe the student should call the university. Or maybe the university should call the student. Or maybe the student is a member of a class, and the university calls the class. And the university just calls the class and say, take the exam. And the class decides how to take the exam. And the class just calls all the students and say, take. They collect the results and then return back the results there. Maybe this way. It's always up to you to decide how to make the composition. Okay, so that was chapter 2. And now chapter 3, the most difficult. Get ready for it, and then we're done. So there are 2 ways how you can think. Actually, this lecture is called algorithms. So in my opinion, the biggest problem for people, for us, which is a bottleneck, which is an obstacle for us when we design object-oriented system, is that we think in algorithms. In our brains, we think like algorithms. We think like step-by-step evaluation of some procedure. So we think, I open the book, I write the letter, I write another letter, I close the book. So we step by step understand how the algorithm should work. And this makes it difficult for us to find the right abstraction inside this algorithm and take it away. I will show you now the practical example, how it can be done, and maybe you will, it's difficult, it takes years to understand how to stop thinking like how to stop algorithmic thinking and how to start object composition thinking or object thinking. So object composition thinking is that when you think like what is the right abstraction to take away from the picture and forget it. Algorithmic thinking is how do I trace my train of thought through all the details of the algorithm. Like I want to go through every single step. Like I want this student to move right leg and then left leg, right, left, and then move the chair and sit down. Next student, next. This is like a super control way of understanding the reality. And object thinking is that I don't care how they move. I just care, take all the students, let them find the places. And then I go to lower level of abstraction. And then I think, okay, now let's think how individual student will think. So this move back and forth from high level of abstraction to lower level, that's the skill you need to develop. Because usually people don't have this skill. They just want to see everything in one long list. Like how everything works, where all my variables, how they stay, who controls who, how the step-by-step moves. But it takes years. So, as software, look at the piece of code on the left. Read it for a second. Okay, I want to close this somehow. But this is this is the result. So, what is the language? Who knows? Nobody knows. Ruby, that's right, that's Ruby. Ruby is actually very much inspired by Smalltalk. It's, in my opinion, the most object-oriented language. Most object-oriented. It's not, unfortunately, so popular now as it was 10 years ago, but in my opinion, it's very, very neat and very elegant. So what it does, this is the variable, buffer, assigns an empty array. This is an empty array. Then while true means endless loop, just endlessly. It reads one character from an input stream. One character. Break if it's an end of line. Okay? Break means stop the loop. If buffer length is more than 3, then print, join all the elements of the buffer. There are 3 elements probably. Print it on the output, on the console, and clean up the buffer. Assign an empty array again. And put the character in the buffer. So this is the output. I do echo hello world, and I run this script through the Ruby. It gives me 4 characters, 4 characters, 4 characters. And oh, it lost the last one. Okay. So that's the way it works. That's the algorithm. This is algorithmic way of describing the intent. It's not object-oriented. Even though Ruby is object-oriented code, this code is not object-oriented. Now I will show you how to make it object-oriented. This very small algorithm. You understand the algorithm, right? So now I will refactor this code, and it will become object-oriented. First, I extract buffer. I make abstraction. Remember abstraction. So I find what is the most suitable abstraction for me. It is buffer. So I take, this is the code on the left. You saw it before, the same. This is the code on the right. So I introduce a new class called buffer. The buffer will be something which takes my data, and when necessary, when it's too large, then it cuts itself, cleans itself, and print the output to the console. So I just extract one abstraction. I think that this is the right one. I make a decision. Could be many other decisions there, but I decided to do it this way. So if I extract this buffer as an abstraction, then this is my code now. Not this one, but this one. This is my code, which is smaller. Now I say buffer equals new buffer, and then while true, I take one character, break if it's end, and then I say buffer push. So now I don't care how buffer works anymore here. So I don't know that buffer will actually take 3 characters or 4 characters, and then it's too many, then it cuts itself, prints to the console. I don't care about these details. This is abstracted away. This is like the student walking into the room. Gone. It's done by somebody. This is the student. It will do it by itself. The buffer. The buffer will do it by itself. This is my first abstraction. I take it away. Now I trust this class. This class will do it. Of course, the code is longer now. You can see more lines, obviously, because for many reasons. But this is inside this buffer, inside this push method, we have the same functionality I had before. If data is more than 3, then print to the console. And you see, these 5 lines are exactly the same as this. But they are moved away from the algorithm. They moved away and they became an abstraction, a buffer abstraction. Okay, that's first step. Second step, loop abstraction. I want to, again, this is the code you saw already with the buffer, and this is my new code. So buffer stays the same. I don't copy it here, so it's the same. I don't, just because I don't have space. So I introduce a new class which is called pool. So pool means take one character from the input stream, return false if it's end of line, and if it's not end of line, then push it to the buffer and return true. So pull is basically the idea that you pull something from the input stream, push it to the buffer, and tell me, do it again or not. So now this is my code. Now it's 3 lines. First, I make a buffer, again some abstraction. Then I make another abstraction, which is called pull, and I do this. While pull again, nothing. Do it again, 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 again. Endless loop. Until again will tell me false. So look at this code now. It's much shorter because I already had 2 abstractions. I took 2 abstractions away. One is something like a buffer. Another is a pool. Well, I call it a pool. That's my name. Just pool is one operation. It's like a student walking into the room. One operation. Pool. Take one character, get in, and communicate with the buffer. So buffer now is encapsulated inside the pool operation. So now we have one higher level abstraction, pool, and lower level abstraction, buffer. And they one encapsulate another. And the final step. No, not final, 2 more steps. So now loop abstraction, I made a mistake, there's the same title. So another abstraction, now I will abstract the loop. The first abstraction was individual pool operation, now the abstraction of a loop. So again, the code on the left you just saw, the same. We have buffer, pool, and the code, and the program. And now we buffer and pool, I don't show you here the same code. I introduce another abstraction, which is called pools. And pools do just the endless loop. Pool, 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 pool. So pools encapsulate an individual pool. And now this is my program. This one line is my code, is my actually program. This is my highest level of abstraction. This is the application. I look at it and I understand what happens. I say, oh, you make pools. Inside that you encapsulate pool, which encapsulates the buffer. And then one call, I say fetch. Okay, fetch them all. So for me, call all the students. How it happens, I don't care. Okay, we go into deeper level of abstraction. Okay, call them one by one. Okay, what do you do with every one of them? Okay, we go even deeper. With every one of them, we send them to the buffer. What the buffer does, we go into the buffer. The buffer does printing and whatever. So my code in the end, this is the final program altogether. So let's look at this. This is the buffer abstraction, the pool abstraction, the pools, and this is my code. Pools, pool, buffer, fetch. So in ideal object-oriented design, the entire application is just a composition of objects and one call and one message, go. One message, call all the students. And then everything just happens. Not algorithmically, like we write most of the code. We still have algorithms in a lot of places where you can look at the code and there are instructions. It shouldn't be like this. You should break down the code into parts which are abstractions for certain things. How you find the right abstractions in your code, that's a big question. How you decide, like in this. It took me a few hours to make this decision. So I was just thinking, okay, what's the right abstraction? Buffer, maybe not the buffer. Pool, how to name it? Actually, finding the right name for the object is the most complicated task. And the more you think about it, the higher the quality of your software. But people usually, we will discuss it on further lectures, people usually give names like utils, controller, manager, all that. These are names. These names actually is actually a signal for us that the developer doesn't understand what exactly is being abstracted. Instead of saying it an apple, the name of the class will be fruit functions or fruit utils. You should think carefully that the name of the class is actually the name of the abstraction from the algorithm, which you decide to take away and call it and give it the right name, like a student, a class, a university, maybe pool and pools, maybe not the perfect names, but I decided to call them like this. Yeah.
Don't you think that in large projects there can be really deep nesting and it will be difficult to maintain the code?
It will be difficult. Yeah, it will be deep nesting. Yeah, I'll show you in next lecture some of my code where this nesting can be like 25, 30 levels, many, and that's good. That means that you have so many levels of abstractions. It means that it will be easy for you to think, because every time you look at the higher level, you ignore everything else. So that's the power of abstraction. If the algorithm is complex, then it's good for you to find what is the higher level of abstraction, so you ignore everything else. And then you go deeper, again ignore everything else, deeper. And when you go down to the deepest level, and at the deepest level you will have like 2 commands. Read the file, encrypt it, return back, something like that. But then you compose into larger, and in the end you have, we have sometimes 20, 30 levels of abstraction. And that's good, and it takes time. It takes time to understand what is the right, and I said it in the beginning, that's a skill you need to develop. You cannot just get it after a few classes.
Why don't you mention interfaces?
Interfaces, first of all, Ruby doesn't have interfaces. That's why they don't have it here. But if I would be doing Java, I would use interfaces here. Yeah, definitely.
Because all this code is just hard-coded classes.
Yeah. In Ruby, you don't have types, interfaces, protocols. They don't have this feature. Yeah. So this is hard-coded classes. Yeah. In Java, this would not be a good design. Definitely, we would need interfaces. But that's for future lectures. Now just understand the idea of breaking down the complex algorithms into abstractions, and each abstraction is trying to hide the data and say, I'm not telling you what's inside of me. I'm not giving you the data. Ask me for the behavior. Like here, ask me to fetch. Ask me, do you need to do it again? Ask me, okay, push me some data. But I'm never gonna return you back, like I do not return my data, for example, to you. I don't return my buffer. I don't, always ask me to work, but don't, like they say, don't, I'll find it later. Tell, don't ask. Ask, don't tell, something like this. Okay, so we have 3 more chapters, they're easy. That was basically it, to just shake you a little bit so you understand what all other lectures will be about. The idea is that people violate these principles a lot. So modern software development, modern open source libraries, they violate everything I just told you a lot. People just ignore it. They either don't understand it, or they just ignore it, or they just think it's not right, or they just came from procedural programming. Most people are quite old and they just didn't learn that when they were in schools, and they just came from C, and they came from languages without objects. They think like algorithms. They still think like a long list of instructions, and they cannot switch to the idea of objects which are abstractions. And we have problems. So who are the enemies of object thinking? Practical enemies. These are 7 things which I decided to talk to you about in the next 7 lectures. So these are things which, if you don't use them, then your code will be like I just explained. You will have proper abstractions, you will properly hide data, and you will properly expose behavior. First, static methods. Static methods are complete evil. You don't use them. That's the bottom line. And the next lecture will be about this. Why, and by example, why static methods? Just forget the keyword static. If you use keyword static, you're just doing something wrong. That's the message for the next lecture. Anemic objects. I mentioned them already. So getters. So every time you see a getter, you know in Java they're popular, getters, setters. So getters are again evil. So if you use getter, obviously you do not hide the data. So you tell, hey, get my data. Of course it's wrong, right? We just discussed. Your purpose, your objective is to hide data. So how come you make the getter? Getter is obviously like, hey, get my data. Don't do this. So every time you use a getter, that's wrong. Number 3, setter. Setter is the mutability. So setter is when you allow somebody to set the data into. It's even worse than getting. Because getting, we can somehow tolerate, and data hiding, we can say, well, we hide, but we can't hide everything. But when you allow people to inject data into your object, that's even worse. Again, we'll discuss why. Workers, that's a very typical mistake people make when they make names for the objects. Instead of saying student, university, Apple, file, user, they say with the ER, controller, manager, printer, reader, streamer, downloader, all of these are wrong. So if you name your class with the ER in the end, that's a clear indicator of mistake. Again, we'll discuss it in the next lectures. Null references. Probably you know it's a bad idea, right? You've heard about it. But I will show you how to get rid of that, how to not use it. So you should not accept null, and you should not return null. You should not say, if the incoming parameter is null, I do this. If it's not null, I do that. That's a bad design. And you should not return null. If somebody is asking you, for example, hey, do you have some data? And instead of returning the data, you just say null, means no data. That's wrong. Again, we don't do that. And I'll explain why. Typecasting or reflection. It's a bad idea in my opinion. Typecasting, you know what it is. Yeah, if somebody gives you Apple and you say, hey, how about I turn you into a file? Yeah, it works. It's okay. In some languages, it may be okay. Or for example, somebody gives you something and you say, I don't know what you gave me. Are you an Apple? Are you a user? If you're a user, I'll do this. If you're an Apple, I do that. That's a very common practice, but we don't do that. That's wrong. And finally, inheritance. Inheritance, in my opinion, again, it's a terrible idea. The way people practice it now. Subtyping is a good idea. Inheritance is a bad idea. And the difference we'll discuss on one of the next lectures. How to pass an exam. So how it's going to work. You form groups of 1 to 3 people. Each group create a software. It can be the software which you created before. I don't need the software to be created for the course. Take the software which you had before. I don't care. As long as it's your software. So I will check. If it's not yours, then we will have problems. If it's your software and it's longer than 5,000 lines of functional code. So we don't count text files, we don't count HTML files, we count code. Written in programming languages, Java, C++, whatever, any programming language you like. So show this and it should work. So it should be something that does something. I don't care what it does. Mobile application, command line application, web server, doesn't matter. Game, whatever you want. It's up to you. And then we'll check. You show this presented and I will check, look at the code. And if it doesn't have static methods, it has no getters or public attributes, it doesn't use null, it doesn't use immutable objects, and it doesn't use inheritance, you get an A. And it will be difficult. I promise you. So try to write the software that way, In the beginning, it was a bit difficult. When down the course, I hope you will start learning, understanding, and maybe you will manage to do it. So it will be difficult to have nothing of that. So probably you will have some, in some places, this or that, and then on the presentation, you will say, hey, yeah, I'm using this because blah, 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 blah. And I will decide whether you really need to do it or you just blah, blah, blah. All right, or another option, just attend 75% of all lectures and you get your C automatically. It's okay, you can attend online. All lectures will be streamed like this one. You can join Zoom. Final one, the read and watch. I tried to find some resources, but I only found David West book and my blog, my video, my blah, blah, blah. So these are the links. I'll send you that later. You can click, read. Hope you like it.